Hi everyone. In the previous week, we have talked about the frequency domain and its response for a given the input. And so we have analyzed the roots of the system, S plus S1 times S plus S2, and then we can represent the whole the things by using these concepts, and then we can have the time response of the system. For example, the electrical system or the mechanical system or any other else. Okay, but in this week we continue with the new one, section 1. So the topic is the modeling in the time domain. That's our concern for this week. Okay, firstly we need to write this thing. Frequency domain has limitations such as we always use the linear system. What's that mean? If the R system is nonlinear, for example, if we have the x dot equal to the x square plus b times x times u, if we have this system, and we cannot analyze this frequency domain approach because we cannot take the Laplace transform of these terms because it's nonlinear. Okay, and also we cannot deal with the time invariant system. This the time invariant means that we cannot depend the time. Okay, the frequency domain can apply to the time invariant system. For example, if we have the x dot is equal to the a t times xt, and then we cannot take the Laplace transform of this term. Okay, because two time variable is or has the form of the multiplication at times xt, and so we cannot take the Laplace transform. Okay, and so also we should say that we have limited applicability of this domain because there are some system for given in the nonlinear form, and then we cannot easily apply this form because it's the ideal form for the systems. Okay, but in real life we don't have any ideal system. Okay, non-ideal system can be arising some problems in here. Okay, but we can also say that we have some useful property in the frequency domain. Okay, we can analyze the transient response or steady state response easily, but in nonlinear system we cannot easily analyze these forms. Okay, we cannot easily find what's the final value of the system for a given input. We couldn't know that, but in frequency domain we can analyze the system in terms of the transient and the steady state response. What's the transient and steady state response? Have you remembered that from the system dynamic lesson? The transient means that it's the first part of the R time response, and steady state is always the constant. Okay, or bounded at the range. Okay.
Can you explain it more? Can you give us an example?
For example, if we have the signal just like this one, t, x, t, okay, and so if we have this signal, and so this is transient, and this is the steady state. Okay, in Turkish this is geçici. It consumes in time. Okay, and so also we can say that this is for tau or the settling time. Just remember that from the system dynamics. Okay, so instead of using the instead of using frequency one or frequency domain, we can build the state space. Can be built. What is state space? Anyone knows that?
A matrix of characteristics of the system.
This state space is a representation of the time domain for a given system. For example, if we have the motor, for example, and so we can obtain the position value or the velocity value or the acceleration value in one form, but we should design whole the system in the matrix domain, because we have the different vectors in here: position, velocity, acceleration, and then we can build the sum matrix to iterate or to obtain the time response of these characteristics. Okay, this is useful for the building in this domain to use state space. Okay, and so if we use the state space in time domain, and then we can model nonlinear system, or we can model the backlash or saturation. We cannot do that in the frequency domain or the Laplace transform, because we cannot add the nonlinearity into this form or into in the frequency domain. Okay, and so we can also give the non-zero conditions, which means that initial conditions can be added to this domain in time response. Okay, and also we can use the multi-input, multi-output system. In state space, because we have for example, the fourth state, position, velocity, and then we can generate the R matrix to obtain the output of these values. For example, the position or the velocity. But in frequency domain, just remember that we have only one transfer function, and so this function generates the one output, right? At the previous week we have talked about it. Okay, and so we should continue with the definition of this term, just like this one, definition. Okay, and so the rules are given in the firstly, let's say the one in here, just like this one. We can select the subset of our system. For example, if we have the DC motor, and then we can assign the theta and theta dot, right? The position and the velocity value. And so we can define the vector in here, just like this one, and so we can build the subset of this system. Okay, and so in another place we can define the nth order system characteristics. For example, we have the theta dot or theta dot or theta, or we have 3 dot operator in here, just like this one, and so we can define this system based on the first order dynamics in state space formation, because at each state we can take the state of this term, and so the derivative of this term is equals to the velocity value, and so we can build another vector in here, theta dot, and then we can build the acceleration in the derivative operation, or we can obtain we can define this dot operator, acceleration vector, and then we take the derivative of this term, and then we get the 3 dot operator in here. Okay, but whole of them is given in the first order domain. For example, z dot is equal to the a times z. Okay, and so we can define the z is equal to what? The theta, theta dot, and theta dot dot. And then we can evaluate the values of the what? The A matrix in here, just like this one. And so this is the first order derivative or the first order dynamics, even if we are using the what? The acceleration, velocity, or the any other operator in here. Okay, this is the advantage of the what? This term. Also, we can give the what? The different initial conditions. For example, we can select the theta 0 to theta dot 0 minus 5 theta dot dot 0 is equal to the 11. Okay, we cannot do that, this initial condition, in the what? In the frequency domain or the transfer function domain. Okay, and so if we are using the state space, and then we can create the denominations or the initial conditions based on these informations. Okay, and so we can condition the system in the what? In what we desire. Okay, just remember that.
I have a question. In context of first order domain, what if we have like x squared? How to convert it to first order?
I will show that. Okay, by using the mass spring damper system. Okay, and so we can also define the algebraic equation. For example, the output equation. Just remember that if we have the transfer function just like this one, tf, and so we can have the x for a given u. Okay, okay, and so but in state space we can define the what? This kind of outputs for a given u or input value, and then we can take the x or x dot or x plus x dot. We can define it by using the what? The sum vector or the matrices. Okay, this is a huge advantage. And so we can take the whole variable from the system, and then we can derive the nib variable or nib vector or nib subset of the vectors by using this property. Okay, any question? If there's no question, and then we should take the example of this term. Okay, example. And so we can define the what? The wall with the specific coefficients of these terms, just like this one. This is what? The mass spring damper system, right? We can define the x deflection rate depending on the time, and so we can give the coefficients of this term. The spring is k and c is the damper coefficients, and then we find out the what? The how can we drive the state space in this domain. Firstly, just remember that we should define the what? The equation of motion, just like this one. Equation of motion of this term is equal to what? The ft is equal to the mx dot dot. This is the preserving energy from these terms, and so also we have the c factor in here, c times x dot plus k times x. Okay, this is what? These are the general equation of motion for a given system. Okay, and so in frequency domain we can say that we take the Laplace transform of this term, and then fs is equal to the m s squared xs plus c s xs plus k xs. Okay, and after that we can refine or redefine this equation by reorganizing all the coefficients, and then we can write that the xs divided by fs is equal to the what? 1 divided by ms squared plus cs plus k. Okay, these are the transfer functions, right? And so we can take the f, and tf is given in here, and we can obtain the x, right? These are the property. But In this system, we have the input value just like this one, f. But the output value, what's the dimension or what is the type of the output in here? Position. And so if we turn into the what this x into the velocity, we should define another term, vs, or another transfer function in here, just like this one, s ms squared plus cs plus k, right? What do we need to add the s in here? Yes, it's a derivative operator, and in Laplace transformation, and then we should add or multiply with the s this value, okay? And so we have two transfer functions in here in frequency domain, but we can also utilize another property or another domain in order to analyze these terms, just like this one. And so the SS or state space is given with the what? With the characteristic of this term. Firstly, we need to write that the x dot dot is equal to the what? The ft m minus cm x dot minus km x. Okay? And so, how can we define the first order system? Based on this information, we have the second order system in here, right? X dot dot, the acceleration of these terms, okay? And so, we can define the dummy variable. Z1 is equal to the x, Z2 is equal to the x dot, okay? We can assign it in here. And so, Z1 dot is equal to the what? Z2, right? And so, what's the value of the Z2 dot? X double dot. And so, how can we write this? Z1 in here, Km times Z1 minus Cm Z2 plus Ftm, right? This is the equation of these terms. And so, how can we write this form in the matrix notation? We should know that we have the vector in here, just like this one, Z, Z1 and Z2, right? And so, if we are using this notation, Z dot is equal to the A, Z, because we have the Z variable in here, and also we have the B matrices in here with the what? The input values, right? The F, right? Because we don't give the what? The F into the what? The A matrix. It's not multiplied with the what? With the F. And so, we should split with what? The SFB in here, okay? And so we can write this term just like this one, Z1 and Z2 is equal to the what? The sum matrices in here, just like this one, Z1 and Z2 plus, and so we have another matrix in here with the what? With the F, right? And so, how can we fill this matrix? What's the dimension of this matrix in here? 2, 2, right? Because we have the 2 times 1 and 2 times 1, and so we should give the what in the matrix operation for the multiplication. We should give the what? The 2 times 2 matrix, right? 2 row, 2 column, right? And so, what's the first parameter of this term? Z1 dot does not include the Z1, right? And so this is 0. And so we have the 1 Z2, and so we should give the 1, right? And so Z2 dot possess the what? The Z1, right? And so K minus K divided by M should be given in here, and also we have the minus C divided by M should be given in here, right? And so we have also a F matrix in here. Z1 dot does not include the what? F, and so we should give the 0. And also Z2 dot includes the what? The 1 divided by M. Okay? And so this is what? This is the state space representation of any system. Okay? And so it always a first order definition. Okay? This is the first order, right? Any question? If you don't have any question, and then we can give the general definition of these terms. The state space representation is the what the z dot a z plus b u in general term. Okay, and so this system in here now is the iterable. You can iterate the system in the time domain to what? To obtain the time response for the what? For every variable. For example, instantly we can take the what? The position and velocity value by using this equation, right? And so this obeys to what? The first order rules of everything. Just remember from the system dynamics lesson, we deal with first order system easily because we can apply the some mathematical rules to be easily in that case. But if we have the second order system, we cannot easily apply the mathematical rules. For example, the stability or the time response or the transience cannot easily obtained from this domain. But if we have this state space representation, and then we can model the motor with the what? With whole state space variable or the state variable, right? And we can take the what? The y cx plus du. This is the state equation, and this is the output equation. Okay, we can take or give the output from the system to what? To outside. Generally, this is the measurement values of this term in real life application. For example, if we have any measurement from the embedded system, for example STM32 or the Arduino, and so if we are using the ADC module, and then you can get the temperature value or the pressure value easily. But if you take this value, and so you can convert to the what? The measurements in this domain. Okay, or we can build this equation in the embedded system, and then we can generate the any other parameters by using this formation. But in transfer function we cannot do that. But this iterable, which means that it's time dependent, and at each iteration we can update the position, velocity, acceleration, and after that we can update the any other parameters based on this information. But in transfer function domain we cannot do that. And so this is easily applied in what? Applied in embedded system. Have you heard of the Kalman filter?
Which filter?
Kalman filter. Kalman filter is utilized to suppress the noises from your measurements. And Kalman filter is based on the what? The state space representation. Okay? Because we can take the every variable from this domain. Any question? Yes. Thank you. C times Z. Okay? So it's the case, and then can give another example in here, just like this one. And so we have the mass spin ampere system in here, just like this one, K1, C1, and Q and F, K2, C2. Okay, how can we analyze this system? We cannot easily build the what? The transfer function in this domain, because we should give the what, the equation of motion based on this information, and then, for example, if we take the movement of the x1 and x2, which is in here, just like this one, and so we cannot easily write the transfer function of this system, because the m1 is dependent on the what, the m2 movements, or the m2 movements is dependent of the m1, okay? And so we can not easily analyze this system based on the Laplace domain, and so we should utilize to what? To state space representation based on the what? The equation of motions of these terms, okay? And so how can we derive this term? In order to solve this equation, firstly we need to give the free body diagram in here. What's free body diagram in that case? What's the meaning of the free body diagram? Have you heard of this? Huh?
Diagram which shows forces.
Yes.
Directions.
Yes. And so we have a mass 1 and mass 2. Free body diagram is given with what, the m1. Okay. And so if we have the direction of the x1 at the downside, and then the whole the vectors is defined at this domain. Okay. And so we pull the m1 to the down. Okay. And after that, if we do that, we have the spring force in here, K1 times with the what? X2 minus X1. I'm sorry, this is the M2. And this is the M2, okay? If we have this information, this is the M2. If we have the force value in here, free body diagram 2, if we take or apply the force at the bottom side, and then this x2 minus x1 can apply the reverse force in here with the same idea, c2 and x2 dot minus x1 should be given in here for the what, the m2, okay? And so FBD1 can also be applied with the what, m1 in here, and so we have the what, the how many force in here? We have the 4 force, 2 of them coming from the spring, 2 of them coming from the what, the damper, right, or the damping ratio, okay? And so we have the what, the K1, X1, 0, because we have the wall in here, because the M1 pulling the down, and so K1 is applied the reverse force at this time, and also C1, X1 dot minus 0, because we have the wall in here, okay, at the bottom side. And also we have the 2 reverse force in here with the what, K2, X1, X2, and C2, X1 dot minus X2, okay? If you are using this formation, and then just pull the mass with the what, with one direction. In the first place, we have the F force value in here. We take the pull to the what, the X2 at the downside, and so this F is given in here. But if we take this M2, and so this K2 resists to move, just like this one. Firstly, X2 is moving, and after that X1 is moving, and so it's the deflection rate should be given in this domain, and also C2 should be given in this domain, okay? And so, in order to solve this problem, firstly, you should divide the free body diagrams, and after that, the mass should be pulled with the what, with the one direction, and so we should find out next the what, the reaction force or the moving force at this case, okay? And so, how can we write this term? We have the m2 x2 dot dot is equals to the what? Our acceleration rate in here, okay? And so we have the F is a positive direction in here, because the x2 is given in here, x1 is given in here, okay? And so this F increase the x2 position, because we have the same direction for both the force and x2, okay? But the k2, x2 minus x1 and c2, x2 dot minus x1 should be given in here, okay? And also m1 x1 dot is equal to every force is given in here is the what? Is the reverse direction of the x1, okay? And so minus k1 x1 minus c1 x1 dot minus k2 x1 x2 and minus c2 x1 dot and x2 dot. These are the what? The elements of our equations, okay? Any question? We have, just I can explain these things in this domain. If we have these spring factors, just like this one, m2 and m1, okay? And so the x2 and x1, if we take this f value, and so we have the direction of the what? x2 is the right? And so if we have this information, and then we can choose these terms, and so f is given in here. It's obvious, right? And so if we take or apply the positive force in here, and then the x2 is accelerated in a positive way. But if we take or pull this m2 to the right, and so this x2 is what? Is increased. And after that the x1 is increased. And so if we have the spring, and so this springs eliminates or prevents the motion from this m2. And so we should give the what? The vector just like this one. Because if we have any spring, and so this always reverse force happens in here, right? And then we should give in here, but what's the magnitude of this force in here? Firstly, we know that k1, right? These are spin coefficients. F equals to the what? The k times x. But in this case, we have the two vector, x1 and x2, right? And so, how can we define these terms? x2 minus x1 should be given in here. Because if we pull the x2 and 2 in here, and firstly, x2 move, and x2 minus x1 is increased. And the direction of this force at the reverse order, or the reverse way, right? This is why we should give the x2 and x1. And this is how we can build the forces or the reactions on this dynamic system. You get it? Just now? No, because the x1 is pulling down. If you pull the x1, and so this k2 creates the what? The reverse force, right? And so this x1 is firstly moved in the first pair diagram, and then x1 minus x2 are the deflection in here. And then we can write it just like this one, okay? Any question? Yes, because in the free body diagram one, m1 is pulling down, okay? This is the rule to create or obtain the whole force in here. Any question? Okay. So these are the equation of motions, and then after that we can write this equation of motions based on the what? These informations. And so Where is the eraser in here? I cannot find it. Okay. Okay. Else are, firstly we have the one equation, and 1 times x1 dot dot is equal to the what? K2 x2 minus x1 plus c2 x2 dot minus x1 and minus k1 x1 and minus c1 x1 dot. Okay. In the second place, m2 x2 dot dot is equal to what? The f plus k2 x1 minus x2 plus c2 x1 dot x2 dot. But in this domain, just remember that we have all the coefficients in what? With the negative magnitude. But in this form, we have the positive magnitude. Why?
We multiply by minus, so it is x2 minus x1.
Yes. We can write the x2 minus x1 or x1 minus x2. And also we can add the what? A negative term or positive term in here. Okay? Okay. And so, in order to build the state space, we can write the what? The x1 dot dot is equal to what? The first x1 should be collected in one form, k2 m1 plus k1 m1, right? And so this is the 1 and this is the 1, right? These terms should be written in the one form, okay? And also x2 is equal to the what? K2 m2 m1, right? Is there another term for the x2 in here? I think no. Okay. And plus x1 dot, which is equal to the what? This term minus c2 m1 minus c1 m1, right? This term is also gone, and x2 dot is the what? This one minus plus c2 m1, right? Is correct? I can order the whole terms x1, x2, x1 dot, x2 dot in here because I should write the state space in specific order. Okay. And so x2 dot should also be given in here, just like this one. We have x1 in here, k2 divided by m1, right? And x2 minus k2 divided by m2, thank you, and x1 dot is here, c2 m2, right? And x2 dot, but we have a negative term, right? c2 divided by m2, okay? But we have also a f m2, right? These two equations are the dynamic equation or the time response equation of the what? Our system. These are the equation of motions. Okay. After that, we should try the dummy variable. Writing the SS is written by with the what? Z1 is equal to the x1, Z2 is equal to x2, okay? And Z3 which is equal to the x1 dot, Z4 is equal to the x2 dot, right? And so Z1 dot is equal to the what? Z3. Z2 dot is equal to Z4. And Z3 dot is equal to the what? The Z1 minus K plus K2 divided by M1 plus Z2 K2 m1 plus z3 minus c1 plus c2 divided by m1 plus z4 and c2 m1. And so z4 dot is equal to what? z1 k2 m2. I automatically write from my notes because our equation of motion previous page. Okay, and z2 minus k2 divided by m2 plus z3 c2 divided by m2 plus z4 minus c2 m2 plus m2. Okay, and so how can we write our state space? Firstly, we should give the z1 dot, z2 dot, z3 dot, and z4 dot, right? And so, what's the dimension of our A matrix in here? 4 by 4, right? And so, we can write together, right? The first term of these terms in here, what? 0 and 0 and no, 1 and 0. And so in the segment Z2 is includes only Z4, right? 0, 0, 0 and 1, right? And so we can also give this comma in here. And after that we are the first term in here minus k plus 1 k2 divided by m1 and k2 m1 and minus c1 c2 divided by m1 and c2 divided by m1. Just write, I'm writing this equation coefficients at a row. See, this is the easiest way to what? To build a state space. And so k2 divided by m2 and k2 divided by m2, but in this case minus given here, and c2 divided by m2 and minus c2 divided by m2, plus we have also the f term in here. And so what's the first row value? 0, second 0, third, fourth 1 divided by m2. Okay, and so this is our state space for the water 2 mass spring damper system. Okay, it's the easiest way for what? For building the whole equation in the one form. Okay, and so let's take a break, and then we will start at the 1 p.m. Okay.